Hi, in this video, I want to talk a little bit about basis states in quantum mechanics. So just like in your intro physics class, when you first were writing down vectors, you chose, in that intro physics class, you probably didn't really know this was a choice, but you chose to write down your vectors, usually expanded in Cartesian coordinates, and using Cartesian unit vectors as your basis vectors. And then perhaps later in your physics career, you might have learned about polar coordinates. And then you said, oh, well, we could also represent these same objects using different unit vectors, namely the polar coordinate ones. So just to write down exactly what I'm talking about here is recall, whenever we write a position vector, we might have some x component, which might be a function of time, x hat, plus some y position, which might be a function of time. And if we're in three-dimensional space, then we'll also have a z component, which is a function of time. And writing these in these familiar ways, this x hat, y hat, and z hat are orthonormal basis vectors. Again, these are probably the first ones that you learned about, but when you moved on in your physics career, you might have learned that we could have made a different choice and instead maybe written these in polar coordinates, where we have some r hat, some theta hat, and then phi hat. Or, even more simply, you can imagine still using Cartesian coordinates, but maybe you rotate your coordinate system to have a different basis, right? This is even assuming we've chosen some origin and chosen a direction for our x-axis. So the same way these are theta hat, r hat, theta hat, and phi hat are orthonormal basis vectors. And so whenever you express a vector in this way, the first thing that you need to do is to choose what basis are you working in. And the way your vector is going to look is going to depend on that basis. And which basis you use often depends on the problem and what is going to be most convenient for that particular problem. Although really any basis is just as good as any other, just what some might be easier to handle. I want to mention these bases are orthonormal, which that really means, so the ortho tells us it's orthogonal, which is to say x hat is perpendicular to y hat, which is perpendicular to z hat. We can also state this orthogonality in terms of dot product relations. X hat dotted with y hat is equal to 0. Similarly, x hat dotted with z hat or y hat dotted with z hat. Right, this is the statement that our axes are orthogonal. And we could write the same thing, r hat, theta hat, and phi hat are also orthogonal unit vectors. The normal part of orthonormal tells us that they're unit vectors or normalized. And this is the statement that they have unit length. We can also state this in terms of our dot product, which is x hat dot x hat equals 1, which is the same as y hat dot y hat, and z hat dot z hat. Okay, with this recollection in mind, let's turn to what we're going to think about when we think about orthonormal basis states in quantum mechanics. So recall we've learned that often this is stated as the first axiom of quantum mechanics is that a quantum state is represented by a normalized vector in a Hilbert space. All right, so we should be thinking about our states as being represented as these vector objects. And remember our Hilbert space, the dimension of it depends on the particular physical system that we're looking at and the number of possible measurement outcomes for that particular thing that we're looking at. So for spin of an electron, which is a spin 1/2 particle, the two measurement outcomes are up or down. So it's a two-dimensional vector space. The vector spaces that we were just reviewing from your intro physics, these are three-dimensional. So we have three of these unit vectors that we need to completely express a general position vector in our three-dimensional space. Here, we're going to want to think about writing down some basis vectors, which are going to be just like our unit vectors from before. The number of them that we're going to need is going to be equal to the dimension of our Hilbert space. So we will need as many basis vectors as the dimension of our Hilbert space. Now, you can write down all sorts of bases that you like, but ones that are going to be most convenient are going to be basis vectors where your basis vectors are associated with definite measurement outcomes. So generally, we will choose, and this is a choice, but it is a very, in quantum mechanics, you almost always make this choice. We will choose our basis vectors to be those with definite measurement outcomes. Associated with a particular measurement. Okay, so I think the best way to start to really unpack these basis states is within an example. And then we'll sort of make more general statements about them after we have an example in the back of our head. So an example are the electron spin basis states. And I say electron, although this example will actually work for any spin 1/2 particle. So any of our fermions, which are all spin 1/2, this would apply to. There are three common bases that one can use, although really one that most textbooks focus on. So one particular basis is the Z basis. These are the two states that have a definite measurement outcome in the Z direction. And we'll write them this way. So the plus Z state, how this state is defined is that this is the state that 100%, if you measure this electron, the spin of this electron in the Z direction, it will 100% be up. And then the minus Z has 100% probability of being down if you measure in the Z direction. So again, this is where I'm saying we're going to choose our basis vectors. They're going to be associated with a particular measurement that we might do. And the particular measurement we're focusing on here is measuring the spin along the Z direction. An alternative basis choice is the X basis. In this case, we're imagining instead we're making a measurement of the spin along the X direction. And this is a totally different basis where these have similar meanings of having definite outcome probabilities in the X direction now. So 100% up and 100% down, but now in the X direction. And in the X direction. And then a third basis we could choose would be the y basis. I'm not going to write it down. It would be the exact same thing. The y basis would have a plus y and a minus y. And those would have 100% probability if you measure in the y direction, right? It would look just like this. Now, it's important to note, right? These are two bases. This electron spin is a two-dimensional Hilbert space. So again, unlike before where we had our three basis vectors, our three unit vectors for our three-dimensional position space that we're living in, x hat, y hat, z hat. Here, we just have two. So we can work with either this basis or we could work with this basis. And those are two different bases. And the same general state that we might have, which could in quantum mechanics could be a superposition state, right? The same general superposition state could be represented either in the z basis or in the x basis. So the fact that these are going to have definite outcomes is related to the fact that they are orthonormal. So these are orthonormal, where again, the ortho is orthogonality. Normal means they're normalized, or really you can think of that as being like unit vectors. And that's because plus z minus z. Remember, we said that the inner product in quantum mechanics tells you something about how similar our two states are. These are two states that are maximally different from each other. Plus z says you 100% will be up in the z direction. Minus z says you 100% will be down in the z direction. So these are as different as you can be. So these two states are said to be orthogonal. And our inner product, again, is sort of like a generalization of the dot product. So we're seeing, again, this looks just like how our unit vectors, the dot product between two different unit vectors was 0. We now have the inner product between two different basis vectors is 0. So these are orthonormal. If we were in the y or the x basis or the y basis, these would also be true. Again, I didn't write down the y basis, but I guess for completeness here, I can write it. So this is the statement that they're orthogonal. What about the fact that they're normalized? This tells us that this is the thing that tells us that they're like unit vectors, right? So the plus z state is 100% the same as the plus z state. So the fact that the inner product of these is 1 tells us that they're 100% identical states. And the same would be true for minus z, or we could say plus x. I don't know why I'm writing these things in the order that I am with the 1 in the middle, but there we go. Okay, so this is the statement that they're normalized. They're 100% the same if you take the inner product between the same ones. So this is the sense in which they're like unit vectors. And so here it's saying that they're 100% identical states. Okay, so more generally, basis states okay, I shouldn't say always. Most of the time in quantum mechanics, you're going to want to work with an orthonormal basis. Otherwise, you really have to interpret things very differently. So for standard quantum mechanics, which is what we're doing, we're always going to want to work with an orthonormal basis. So general orthonormal bases. So we might have, so again, for an n-dimensional Hilbert space, we need n orthonormal basis vectors. And so we can say we have some set, which here I'm just is like 1, 2. I'm just labeling them 1, 2, 3 because depending on what physical measurement you're looking at, you might name them different things. But we have n of them. This is our set of basis vectors. The fact that they're orthonormal means that ij in our product should be equal to a Kronecker delta, right? Because this means that ij is equal to either 1 if I equals j. So that's again if we're taking the inner product between two of the same basis states, or 0 if I is not equal to j, in the case that they're orthogonal. So this is the general thing that you want to really remember about basis states. And then any general quantum state can be expressed as a superposition of basis states. So our general physical state psi can be written as a sum from I equals 1 to n, the dimensionality of our Hilbert space, of some coefficients times the basis vectors. So this says C1, 1 plus C2, 2 plus dot, 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 Cn, n. This is exactly like, again, in your intro physics class, where if we work in Cartesian coordinates, any position vector can be represented as a sum over our Cartesian unit vectors, right? Any vector can be represented this way. So in the same way, and hopefully my iPad, oh, it just erased things. But you can rewind in the video because we're pretty much done. Any of our quantum states can be written as a superposition over our basis states. So I'll write down the last thing I'll say. So again, in this spin example, any spin state of the electron can be expressed as psi equals some coefficient plus some other coefficient times the down in the z state. Or we can say, I don't care so much about the z direction. I'm more interested in the x direction. This same state can be written as a superposition over the x direction. Right? These can be the exact same. Oh, this should be a B here. The same state can be represented in the same ways. Just like in your intro physics class, you could represent the same position vector in Cartesian or polar coordinates. Here, we can represent the same physical quantum state with z basis vectors or with x basis vectors. And I'm sorry, I'm making all sorts of typos. This should also be a minus x, right? With coefficients. These coefficients, of course, will depend on which basis you're working on. So that's why I chose B's and C's to remind you that they're different. Okay, so we're always going to want to, when we're thinking about a quantum mechanical system, and we want to think about the states in the system, generally the first thing you want to do is say, okay, what is some measurement that I could make on the system? What are the possible outcomes and how many of them? However many outcomes you have is the dimension of your Hilbert space. And then you need a number of basis vectors equal to that number of possible outcomes, right? So you want to span this whole n-dimensional space. And we're going to span it and we're going to, quantify this space by choosing basis vectors which have definite values for that particular measurement that you're focusing on. Okay, so that's the basics of basis states.